This set of notes is about integrated rate laws. As always, you have a set of notes printed for you, or you may use the digital set that's posted in Schoology. Okay, so in terms of kinetics, things that we've done so far is we know how to identify the factors that affect the rates of reactions, right? What makes reactions go faster and slower. We've been able to figure out how to calculate reaction rates from data and balanced equations. We've also learned how to write and identify the order of rate laws. And then last but not least, we've learned how to use initial rates to figure that out. So what we're going to be doing so far, or next, is we're going to be going ahead and saying, okay, let's say we're not talking about the concentrations rate at the beginning. What happens if we want to follow the concentration through a reaction and figure out what the concentration is at different times as a reaction proceeds? How do we figure that out? Okay, well, that brings us to the concept of integrated rate laws. So essentially the idea here is you take the rate law that you write for a chemical reaction and you go ahead and you integrate it using calculus from doing an integral from time 0 to time t. Okay, so now I hear you possibly all out there freaking out about calculus right now. Do know that for the purposes of our course, you don't actually need to know or do the integrations. You don't have to do calculus for this at all. You just need to be able to identify and manipulate the equations that result from that integral. Okay, those are on your pink sheet. If you are a calculus superstar and you really want to know where these equations are coming from and how the calculus is done, there is a calculus discussion in your notes that I printed out for you and included in there. That is totally optional. You don't need to do anything for it. It's just every year somebody asks me, so I included it. All right, so as we work through this, do remember that when we're talking about reaction rates, if we're talking about something in solution, we're obviously going to be using concentration, but we can replace that with pressures of gases if it applies to a particular situation. Okay, so wherever we see concentrations of some things in here, know that can also be the pressure of something in here. All right, so if an order is overall first order, and we go ahead and we integrate that rate law, what you're going to end up with is a equation that looks like this, where A naught is the initial concentration of A at the beginning of the reaction, and A is the concentration of it at some point T. Okay, so that is going to be related using a natural log relationship. If we go ahead and we manipulate that equation around, what we can do is we can eventually get it into a format that looks like this using our logarithmic rules. Okay, and so what that basically tells you is that we've got a y equals mx plus b form now, which means that this is a linear equation where k is the slope, m, and the initial concentration, or the natural log of the initial concentration, is the y-intercept. So graphically then, if you go ahead and graph out this equation, if a reaction is first order, the natural log of the concentration versus time is going to be linear, and the slope is going to be the negative of the rate constant. All right, so here is a reaction, the reaction of methyl isonitrile to acetonitrile. And so we're going to go ahead and think about that particular process of making this reaction go. And if we went into the lab and we actually took data of the pressure of the reactant over time, what we would see is we would go ahead and see a graph that looks like this. Okay, so this is the pressure or the concentration versus time. However, if I go ahead then and replot that, taking the natural log of all of the pressures, we see that it becomes a straight line. Okay, so in this particular case, the natural log of the concentration is a linear function, and as a result of that, we know that this reaction is a first order reaction. We can also go ahead and look at the slope of the line that results, and we can use that to figure out the rate constant K. So in this particular case, if we did the mathematics, we would see that the rate constant is 5.1 times 10 to the negative fifth per seconds. If a rate law is second order for a reactant, Then going ahead and integrating that rate law would go ahead and give you a equation that looks like this. Okay, if we do the same kind of manipulation we do previously, we can see that this also becomes a y equals mx plus b equation. Okay, so again, in this particular case, m is going to be our rate constant, and so that's the slope of our line, and 1 over y is what becomes linear. So therefore, if a reaction is second order, 1 over the concentration of A is versus T is linear, and the slope of the line will be our rate constant. Okay, so here's another reaction. This is the decomposition of nitrogen dioxide or nitrous oxide into nitrogen monoxide and oxygen. And this is monitoring the concentration of the reactant NO2 over time as things go on. And if we go ahead and we plot that out, we would get a graph that would be nonlinear. However, if we take 1 over each of these concentrations and we graph that versus time, we end up with a nice linear graph that looks like this. Okay, so we would go and we say, all right, 1 over NO2 squared is a linear function, so it's got to be second order. And I want to figure out the rate constant. The rate constant is the slope of that line. There are also situations where the rate constant is not dependent, or the rate is not dependent upon the concentration at all. So that would be rate equals the rate constant times A naught to the 0th power, right? Which is basically 1. So in other words, the rate equals the rate constant. And if I go ahead and integrate that, I get this equation, integrate it and linearize it, I get this. So once again, it is a linear equation. So m, the slope of the line, is my negative rate constant, and graphing the concentration of A over T becomes linear. Okay, so again, doing the calculating and just graphing concentration over time gives me a linear equation, and again, the rate constant is going to be the negative of the slope of this line. All right, so we refer to these as the graphical methods to determine rate orders. And so again, if something is 0 order, it's the concentration versus time that's linear. If something is first order, it's the natural log versus time that is linear. And if something is second order, it's 1 over the concentration versus time that is linear. Okay, and again, in the ones where the slope is negative, that's the negative of the rate constant. In the one case where the slope is positive, that is the rate constant. All right, so an application of this is the use of half-lives. All right, and by definition, half-life is defined as the time required for 1/2 of the reactant to react. All right, so if I look out over here at our graph, I start with 150 torr of pressure of this. I would know that half of it's reacted when I have half as much, at 75, okay? So that's a particular time, and if I look here, it's about 12,000 seconds, right? So again, the half-life is how long it takes for half of the reactant to react. So if I start at 75, and I wait for it to react half as much again, down to 37.5, and I look at that time, you'll notice that's 24,000 seconds. Or in other words, every single time that we have half as much react, 12,000 seconds goes by. So that then 12,000 seconds would be our half-life, okay? So because the concentration of A at the half-life is 1/2 of the original concentration, we can look at this and say at this particular situation, concentration at the half-life is 1/2 of the initial concentration. Okay, if I combine that then with a first order reaction and take that into account where I tell us that A of T, or the concentration, is half the initial concentration, I can sub that in, and by doing all of the substitutions down through here, what I end up with is that the half-life is this number, 0.693, divided by the rate constant, okay? And that has to do with it, natural log of 1/2 coming in there, okay? This reaction, or this equation, is in our pink sheet. And the thing that is interesting about this is that if you have first order reactions, their half-life is independent of a concentration. So this is another way of identifying that something is a first-order reaction, is if its half-life is not dependent upon the concentration of either chemical. We contrast that with a second-order one, which, if we go through the exact same process with a second-order integrated rate law, we find that the half-life of a second-order reaction is 1 over the rate constant times the initial concentration. So you'll notice that in a second-order reaction, rate is dependent upon concentration. Okay? You do not need to know this piece of information or do any calculations with this. It's not part of AP curriculum. It will not be tested. Primarily, I just put it here to contrast it with first-order reactions, because you will be asked things along the lines to say, oh, the half-life isn't dependent upon concentration. What order is this? You need to be able to go, oh, that's first order, because in a second-order reaction or another order reaction, concentration would matter. Okay? All right, that's what you need to know about integrated rate laws.